Okay, so now we're going to talk about planes, and well, you can think of a plane as an infinite sheet of paper, and that would be useful because when in calculus, right, when you had a function whose graph looks like a curve, when you found the derivative of that function, you would say that that gave you the slope of the tangent line to a point on the curve. So curves were important in calculus because in a sense at each point on the function for the on the curve you could approximate the function with this tangent line. And if you just look very close to a specific point, the approximation is really good in general. In a couple, I guess, of days or videos, depending on how you're counting this right now, we'll have functions of many variables. So here maybe you had y equals f of x, but now there will be a function of, say, of two variables, y equals f of xy, sorry, z equals f of xy, and here it's not so convenient to think of trying to find like a tangent line, rather because the graph is now two-dimensional in a sense. You want to think of finding like a tangent plane. Okay. And so again, the point is that the tangent plane will be a good approximation to the graph when you just look very close to a specific point. And so we need to get a handle on planes in the same way in which we had to know some facts about lines when you were studying the problem about finding tangent lines. Okay? So again, you should think of a plane as some infinite sheet of paper. So if you have something like this, a plane would take this form, or maybe a tilted version of this. You can rotate it around. And so one of the things we would like to do first is find an equation for this plane. Okay? If you remember from the videos on lines, for a line you had to specify a point on the line and a direction vector, right? Here there's a way to think about planes. One way to think about a plane is that a plane consists of a bunch of lines, right? If you think about it from that perspective, say in order to specify a point in order to specify one of the lines, you would need a point, and you would also need a velocity vector, right? So you can think of this as like you're driving along this particular line, so you need a point and a velocity vector to specify it, but maybe you want to switch lines and you want to drive in another line. So in order to switch lines, you need another vector which is sort of complementary to it. Again, if you take linear algebra, the idea is that it's linearly independent, but it just means that it does not give you the same information as this vector. So say you could take, for example, although it's not necessary, you could take another vector u, which in this case it looks perpendicular. Again, it's not important for it to be perpendicular. It just doesn't mean cannot be parallel to v. But the point is that this other vector will tell you how to move between lines if that's what you wanted to do. So what that suggests is that in order to specify a plane, for a plane you need a reference point P, which is what we used before. And then you also need two direction vectors, which you could think of them as being velocity vectors. That's fine. That's not indispensable. So two direction vectors, which I'm going to call U and B, as in this picture. And so basically, as you might guess, if you have any point on this, the position back, if you take a point on this line, right, there's a position vector for this point. So if you were just, so one way to think about it is that in order to specify this point, you can start from P, you move to this point on this line, and remember that in order to do that, you do P plus TD, right? That was the equation of a line from before. But now maybe this point that you chose is not on this particular line, so you have to use you need the help of U to finish moving towards that point that you really care about, and that takes you some other amount of time, right? Some other displacement, which you could also call TU, but I mean, like it may take you different times you may use different amounts of time to get first to this point and then to this other point. So you will use another letter like SU. And so that's the equation of a plane, the vector equation of a plane. Now, this equation for the plane says that in order to specify any point of the plane, you sort of need two variables, t and s, because p, v, and u have been given to you, right? They're like sort of constants in this equation. Those are known data. That's like part of the input data. And t and s are the things that you can change as you need in order to reach all the points in the plane. So really what this is saying is that a plane is something that needs two variables in order to be specified, while on the other hand, a line just needs one variable, right, which was the variable t. So once we reach the end of the course, what you would say is that like something like a line just needs one parameter, and something like a plane needs two parameters. Now, again, like this formula is fairly easy to use, so if you wanted to use it in practice, say like I would give you give you a point and then two direction vectors, and then you would just, if I asked you to find the equation of the plane, you would just use this formula. So the equation of the plane would be r equals p, which is 1, -1, 2, plus t times d, which is 2, 1, 3, plus s times -1, 1, 1. Okay, so this is not terribly difficult. Now, the thing is, like, for now, it's not that convenient for us to work with this format of the equation of a plane, there's an equation which is more similar to the usual y equals mx plus b equation of a line, which is the one that we will exploit right now, and that uses a normal vector. So the point is that let me just show you the idea. So think of this is a plane, right? This is like an infinite sheet of paper. I'm saying that in order to specify the plane, you needed these two vectors, u and v, which sort of give you directions for motion along this plane. Again, they don't need to be perpendicular to each other. They just cannot be parallel. So there's a lot of wiggle room that you have in order to specify these direction vectors. But now, in order to know, like, really, instead of knowing these two vectors per se, you just need to have the information about a third vector, which is one that you can create from out of these two, which is what's known as the normal vector to the plane, and that's a vector that's perpendicular to the plane. Okay, which is the one that you see here. So given two direction vectors, you could take, for example, their cross product, because remember that the cross product is perpendicular to the original vectors. And so the cross product of these two direction vectors will specify a vector that's perpendicular to every point on the plane. And that, together with the information about the reference point, suffices to know completely where that plane is supposed to be located in space. So let me just give you an alternative description of a plane. Using the normal vector. And the point is that in practice it's better just to find one vector than two. So it's, in a sense, it seems like you're carrying less data, but it's actually ends up being equivalent to it, to just knowing the two direction vectors. But again, the idea is that if you have a plane here, imagine that I know a reference point P as before, and I want to know the equation for any other point R here. Let's call this point Q. Okay, so assuming that we know, that means that there's a position a relative vector that goes from P to Q, which is a vector PQ, and then a normal vector to the plane, well, it's a vector that makes a 90-degree angle with any vector that you can draw on the plane. So maybe as an illustration, what I'm trying to say is that imagine that here's point P, here's point Q, then there's a displacement vector that connects them, right? Which is the one that you see here. But then the property of a normal vector is a vector that's perpendicular to all the displacement vectors that you can draw on the plane. So in particular, it will be perpendicular to this specific one that I drew on the board. And so the point is that the normal vector n has a property it's almost by definition that it has this property. That it is perpendicular to any displacement vector that you can draw. Remember, being perpendicular is the same as saying that their dot product is 0. So the one of the advantages of having dot product is that you can just write algebraically things that otherwise you would need to say using words like saying, oh, they're perpendicular. Now you can just express this as an equation. And so what does that translate into? Well, let's say that this point, okay, let's just use some notation. Usually, again, the data n, the vector n is given, so let's say that it has components a, b, c. P is given, so let's say it has components x naught, y naught, c naught, and x and q is not given. That's what we're trying to find. So it has components x, y, and z, because those are the ones that we don't know. And so the equation n dot pq equals 0 remember that PQ is the same as Q minus P, or strictly speaking, the position vectors, the difference in position vectors of these 2 points. But that is the same as n dot Q minus n dot P equals 0. And that's the same as saying that n dot Q equals n dot P. And what is n? N is ABC. What is Q? That's x, y, z. And what is n? ABC. What is P? Is x naught, y naught, c naught. And so you get the equation of the plane, which reads, this is the usual way in which you see it. It's like ax plus by plus z z. Let me just use British pronunciation. Z equals ax naught plus by naught plus c naught. Okay. And this is the right hand side is some known junk, so you just call it D. So this is known to you, so call it D. So let's again do an example, just exploiting this equation. So again, if I wanted to find out the equation of a plane, now I will now give you a point, say 1, -1, 2, a vector n, say 2, 1, 7, and maybe the equation of the plane really, I think, is easiest to remember as n dot xyz equals n dot p. That's the easiest way to remember it. And so you would say that 217 dot xyz equals 217 dot p 1, -1, 2. So you get 2x plus y plus 7 z equals 2 minus 1 plus 14, and so you get 2x plus y plus 7z equals 15. Okay? And there it is. That's the equation of a plane. And notice that this looks more similar to like y equals mx plus b, right? So it's like in a sense like a useful generalization of the equation of a line. And one of the features of writing the equation this way is that these coefficients, if you notice, you get 2, 1, 7. So from this equation, you can read the normal vector. So from the left-hand side of the equation, give you n. So meaning that if you had another equation like minus x plus 2y plus 3z equals 5, that means that n has to be here negative 1, 2, 3. Okay? So that's one useful thing to know. Maybe I should just say in words or write it out. Like n is not necessarily unique. I mean, n is not unique. Just in the sense that this equation, I mean, if you take this equation and multiply both sides of this equation by 2, you get minus 2x plus 4y plus 6z equals 10. Right, but I mean, these are representing the same plane, right? Because they are just the same equation. I could divide by 2 both sides. And so, but obviously here, you would rescale that normal vector by 2, so you would get negative 2, 4, 6. And so that means that you only need like some vector that works as perpendicular to the plane. You don't need it's not just that a single vector will work. There's more than one choice. Okay? And then one of the useful things that you can do once you think in this terminology is that you can talk about parallel and perpendicular planes. So parallel planes would be planes whose normal vectors are multiples of each other, and perpendicular planes will be planes whose normal vectors are perpendicular to each other. So let me just write that down. Meaning that you can rescale one vector to get the other. Again, it doesn't necessarily require you to say that they have to be the same, because we already saw that there's more than one choice, so it would be too much to ask. What you only need to ask is for them to, like say, that if you have one normal vector, you multiply it by 3 and you get the other normal vector. If that happens, the planes are parallel. And the other extreme situation is where the planes are not parallel but rather perpendicular. Or orthogonal planes. Okay, so if the dot product of the normal vectors is 0, then you say that the planes are orthogonal. And as you can see from this picture, like in general, what this image suggests is that when the two planes intersect, they will intersect on a line. They don't have to be perpendicular in order for that to happen. So in the next video, I'll do an example for you where we find the intersection between two planes.